So I want to end this week and this course with sharing a few of the very kind of weird, quirky, if you will, particles that scientists have discovered over the last 50 years. And this is kind of the most cutting edge, most modern part of the course. It doesn't have a heck of a lot of an implication for biology and life science, but it is kind of interesting just to know what are the other really small things that make up everything that most people don't necessarily know about. So one of those interesting particles is called the neutrino. And you might remember that I told you that there's 5 conservation laws that need to be fulfilled when there's radioactive decay. And if those conservation laws are not fulfilled, then something's wrong. Well, in 1930, Wolfgang Pauli looked at the beta decay and realized that something might be wrong here because there was a conservation law that wasn't satisfied. And in order to satisfy it, he hypothesized the existence of a new particle called a neutrino. Now it's called an electron neutrino. So the neutrino has no charge, has a very tiny mass, and travels very close to the speed of light, which makes it incredibly hard to detect, which is why it was not actually discovered until 1956. Today, however, neutrinos are created in abundance in nuclear reactors and particle accelerators and are thought to be plentiful in the universe. And since they have no charge, it takes very elaborate experiments to detect them. And you could see this gnarly neutrino detector in Japan that they had to create just to be able to find and see these things. Now, what makes neutrinos kind of interesting is that there is a lot of attention on them as potentially what may make up a lot of what we call dark matter. So there's this issue where we realize that galaxies are forming in ways that suggest that there must be a lot of matter out there that we're not seeing, and that for whatever reason is hidden to us. And neutrinos, since they are so difficult to detect, are a strong candidate for what might make up at least some of this idea of dark matter. All right, moving on. Positrons and antiparticles in general. So it turns out that for every particle that we have, like a proton and an electron, there are antiparticles. So like the anti-electron is called the positron. Right? And then an antiparticle for a proton is called an antiproton. Okay? And there is a tremendous mystery to these fellows, right? Because when for example, an electron, right? Let's say I have an electron, right? And it's, cruising this way. And let's say that I have its antiparticle, the positron, right? So this is not a proton, it's a positron. So same mass as the electron, but opposite charge. That's what the anti means. The anti means opposite charge, okay? So same exact particle, we have a particle and its antiparticle, right? And they hit each other. What happens is they annihilate each other and some gamma radiation comes flying off, right? So a gamma particle goes away, all right? This is interesting because it begs the question why we live in a universe that had more particles than antiparticles, right? Because if the universe was born and we had an equal amount of particles and antiparticles, then the whole thing would have annihilated itself. We'd have all this gamma radiation, all right? And we wouldn't have any of the particles that we need to form stars, which then contribute to forming planets, which then contribute to forming, solar systems and galaxies and all the stuff that makes the universe look the way it is, right? So there are these theories that there was this slight asymmetry between the number of particles and antiparticles at the beginning of the universe. Like for every billion antiparticles, there was 1,000,000,001 particles, such that 1,000,000,000 antiparticles canceled out and annihilated 1,000,000,000 particles, leaving one particle left that could survive. So in other words, that there was so much more matter originally, shortly after the birth of the universe. A ton more matter, but a lot of it was antimatter, and those collided with each other, and as a result, created, all this energy, but left a tiny bit of matter. But that tiny bit of matter was still enough to create all the matter that we see in the current universe, which is fascinating to think about. Now, here's something else is interesting that makes studying antimatter so difficult, and that is that you can't put it in a jar, right? It's not like you can just contain it. The only way you could contain it is actually with what's called electromagnetic containment, which is where you're able to, hold a particle in place using electromagnetic forces. But the thing is, what would happen if you had a jar of antimatter? Okay, if you had a jar of antimatter, it would annihilate the matter making up the jar, and the whole thing would explode, and you wouldn't be able to see anything. So this continues to be an interesting area of research and exploration in physics, and thought I would share it. Okay, the next set of particles that I want to talk about are the quarks, which are actually the building blocks of the nucleons. Okay, so in 1963, a quark theory was advanced. Obviously won a Nobel Prize. The theory proposed that there are 3 quarks and 3 corresponding antiquarks that electrons, protons, and neutrons are constructed from in various combinations. Thus, the quarks are elevated to a status of elementary particles. The 3 quarks were named the up quark, the down quark, and the strange quark. I love modern physics because you could be so playful with the names. Confession, a big part of the reason I entered physics was because I loved the kind of playful names, because these things also have characteristics of charm, color, and various other just fascinating like names and quirks that make up the properties of these particles. Okay, so in other words, quarks actually have plus or minus 1/3 charge, because 3 of them form particles, the nucleons like electrons and protons. And so a quark possesses a charge magnitude smaller than that of an electron, which has a charge of negative E. There's a list here of symbols and electric charges of these quarks and the corresponding antiquarks. So you can just check that out in that little table. Experimentally, quarks should be recognizable by their fractional charges. So you've encountered a quark if it's exhibiting electrostatic forces, repulsion, but not to the magnitude that you would expect for an electron or proton. But in spite of the extensive search for them, free quarks have never been found. So we've actually never found a free quark out in the open. And if you were to do such a thing, you would probably win a Nobel Prize overnight for it. Lastly, I wanted to share with you this picture here of the standard modicle of particle physics. This gives us the fullest description of all the subatomic particles and the subatomic universe that, as we know it to be, all the quarks, the difference between fermions and bosons, which, remember, fermions have half integer spin, whereas bosons have integer spin. All the different regimes for the different types of particles, and this right here is the very cutting edge of everything that we understand thus far about physics and the research to come in this world that helps us understand what is really the foundational structure of all forces. What is the structure of the subatomic world that explains gravity and also explains quantum physics at the same time, because right now those two worlds are colliding. And you may have heard something called the grand unified theory, or the theory of everything. That is the next step in this whole process. We've found ways to unite electric and magnetic forces, and we found ways to unify that with the weak and strong forces as what's happening here in the Standard Model, but we haven't found a way to unite that all with gravity. And if any of you decide to leave biology and enter this world of subatomic particles, you could be part of this quest to discover the ultimate blueprint, the theory that makes up the foundation of life itself, and the world itself, and the universe itself. So with that said, I encourage you to stay curious and to keep exploring these questions and explore your curiosity where it leads you. And if you ever have anything to celebrate, let me know.